All right, today we are going to be talking about inductors. So inductors are the first element that we are going to be dealing with that serve as a form of temporary energy storage in a circuit, which implies that they are capable of supplying some amount of power. Okay. So a little bit of background, if we have a wire, and this wire is carrying some current, I, then what we will observe is that a magnetic field will wrap around the wire. And the direction of that magnetic field is given by what's called the right-hand rule. So if your thumb, for those of you that have had Physics 202, this is probably review. But if your thumb is the direction of current flow, the magnetic field curls around in the direction of your fingers, like so. So effectively, we get these little loops of magnetic field curling around the wire. And that magnetic field carries some amount of energy. Okay. So an inductor exploits this by coiling the wire effectively. So consider the following two scenarios. In the first one, we're going to have a cylinder. And we're going to simply wrap a wire around it. Like so. If we were to pass some current through the wire, we would wind up observing what I'm going to call magnetic flux that is being compressed into the interior of this coil. Okay. So these arrows right here are representative of the magnetic flux, where magnetic flux simply means the amount of magnetic field that's passing through a particular surface area. Okay. So when we coil the wire in on itself, effectively everything inside the solenoid is going to get compressed. And so we have a lot more magnetic field in that area, and we are storing energy by maintaining that magnetic flux inside that coil. Okay. There are a couple of other key figures of merit. We're going to have N turns of wire. So that's telling us effectively how many coils we have. And this red thing right here is what's called the core material. And depending on what the material is, it can either enhance the magnetic field or decrease the magnetic field inside of this solenoidal coil. The second most common inductor configuration is the toroidal coil, where toroid is just a fancy word for donut shape, effectively. So if we have a donut-shaped core around which we wrap a wire. Like so. And we pass current through the wire. Once again, we will see that we are compressing the magnetic flux inside this core material and storing energy. We also have some finite number of turns. These are still magnetic flux lines, and everything in red is still a core material. So it's just two different variations of effectively the same thing. All right. So inductance L is defined as the ratio of the magnetic flux which is phi b, divided by the current which causes the magnetic flux, I. Okay. So it is a constant of proportionality between these two quantities, much like resistance is a constant of proportionality between voltage and current. Okay, so that's all inductance is. Now, magnetic flux mathematically relates to voltage due to a thing called Faraday's law. So Faraday's law says that the voltage drop across a coil like this is equal to the derivative of the magnetic flux as a function of time with respect to time. And since we know that the flux is related to current by the inductance, this becomes L di by dt. So this is our first relationship. The voltage drop across an inductor is related to the derivative of the current flowing through the inductor multiplied by the inductance value. Okay. There are a couple of different implications buried inside this mathematical expression. The first of which is for DC circuits, an inductor behaves like a short circuit or wire. So effectively, if the current doesn't change, the voltage drop across the inductor has to be zero. And the only circuit element we know of that carries a current while maintaining zero voltage across it is a short circuit or a wire. So in any DC circuit that you guys are asked to analyze, and you will have some to analyze that contain inductors for this homework set, simply treat every inductor as if it was a wire and then move on about your day. Now, whenever the current changes, that's when things get interesting. And we actually have to start using a little bit of calculus in this class. Okay. So the other thing that we can glean from this mathematical statement, V is equal to L di by dt, is that the current flowing through an inductor cannot change abruptly. So what I mean by that is that our current waveform, if it's a time varying signal, can't instantaneously change from one value to a different value. So let me explain what I mean by this with a little bit of math and pictures, okay? So let's consider this graph on the left-hand side to be our current waveform, and the graph over here on the right-hand side will be the resultant voltage waveform. And we're going to look at a couple of different cases, so I'm going to be lazy and copy these axes here. So let's say that our current waveform looks something like this. We have a linear increase in current until sometime t1. Our current stays constant until sometime t2. Oops. Our current decreases to 0 until sometime t3, and it stays 0 after that point. All right, and we're going to call this I max. We're not worried too much about numbers here. We're just looking at how this thing is going to behave, okay? So in the region from 0 to t1, the derivative of the current is going to be a positive quantity because the current is linearly increasing, right? So there is some finite slope, and that slope is positive. So what we should expect to see from our equation is that since our slope is a constant value, we're just going to multiply that slope by L, and we get our voltage. So the voltage, let's say for the sake of argument, would be something like this. Until T1, here's T2, here's T3. We're going to talk about the other bits now. For the interval T1 to T2, what's the slope of the current? 0. And since the slope of the current is 0, that means the voltage drop across the inductor is 0. So our voltage will drop abruptly down to 0, and it will stay 0 the entire time the current flowing through the inductor is constant. Over the interval from T2 to T3, our slope is negative. And so we're going to get a negative voltage. So let's call it, graphically represent it with something like this. Oops, my screen keeps sliding away on me. And then for time greater than T3, since we have a constant value of the current, we have a 0 value of the voltage. Okay. So what would happen if call this T1, T2, T3 again. Our current waveform looks something like this. Effectively, at its maximum, we're pushing the same amount of current through this inductor, but our slope is much more steep, right? So if the change in current is much steeper, what should we expect to see for our voltage waveform? Higher voltages, absolutely. So in this case, we'd probably see something like this. The magnitude of the voltage would be much higher. So if we take this phenomenon to the extreme and we allowed the current to instantaneously change from some low value to some high value, what would happen to the voltage? It'd be infinitely large, right? So if we, let me do this in a different color here. If we had a current waveform like so, to where we effectively instantaneously changed from some low value up to the maximum value in an instant in time, we would see that we would create infinitely large voltages, which obviously cannot happen because voltage is a measure of energy transfer in a system. And we cannot transfer an infinite amount of energy in an infinitesimal amount of time. So that is why the current flowing through an inductor cannot change abruptly. So what that really means is that if you look at an instant in time, the current immediately preceding that instant in time and the currently immediately after that instant time have to be the same thing. So this isn't saying that the current can't change, it just has to do so in a gradual and well-defined process. Effectively, our current needs to be a continuous function of time in order for the laws of physics to not be broken, okay? Now, let's talk about what really happens if you were to do something like this. How many of you guys have used a hairdryer before? Several people have used hair dryers. How many of you have unplugged a hairdryer while it was on? What happens? Sparks. So the sparks that you see when you unplug anything that uses an induction motor while it's still running is effectively it trying to maintain the level of magnetic flux that was flowing through its coil at the instant before you unplugged it. The voltage that's being generated is so large that it is literally ionizing the air particles and forming a local plasma. That is what those sparks you're seeing is. You can get astronomically large voltages by trying to force the current to change in an inductor quickly. And the amount of energy that's required to ionize air is something on the order of 100,000 volts or something like that. Like it's very, very, very large. It only lasts for milliseconds to microseconds or things like that. But that's how strongly an inductor wants to keep the magnetic flux constant within it, okay? Now, that's actually also how it's used as a form of temporary energy storage. When you get some amount of flux stored within it, you have stored energy. And when you allow it to release, you are injecting that stored energy back into the system. Okay, so it's working how it's supposed to effectively when you see those sparks. You're just not giving it a particularly good outlet to release that energy back into the system. All right, so we have this first equation. Now what we're going to do is mathematically rearrange this equation and come up with our second equation. Okay. So if we start with the voltage drop across an inductor is equal to L times the derivative of the current flowing through an inductor. Well, if we multiply both sides by dt, let me give myself some more room there. And what I'm going to do now is I'm going to divide both sides by 1 over L, or excuse me, divide by L. So I'm going to have 1 over L if I integrate both sides, we can find out what the current through the inductor is if we know how the voltage behaves. Okay. Now we need to put some boundaries on this integral. Okay. So the first way that we're going to look at this is from negative infinity to some point in time t that we are interested in. And then that forces me to call this t prime here and here. Not there actually, because I can't have the same variable inside my function as I have in my limits of integration. So that's just mathematical nuance there, okay? Now, how do we know what the current flowing through the inductor was, or how do we know how this thing is behaving at negative infinity? We probably actually don't. We have a good idea, it should be 0 and things like that. A more common representation of this particular expression is the current flowing through an inductor is the integral from T naught to T of VL T prime dt prime plus IL at T naught. The form of this integral is very similar to what we saw for charge way back on the second day of class. This IL of T naught term is the initial condition. So it's a known quantity or a measured quantity at some particular point in time. So we can say to some extent that inductors exhibit memory because their current behavior depends on their past behavior. So the value of current flowing through an inductor right now depends on the amount of current that flowed through it previously, okay? So this is going to be our second equation. Now, we'll develop a couple of more. So the power that's absorbed by an inductor is, what the hell happened there? Is by definition, the current flowing through the inductor multiplied by the voltage drop across the inductor. Power is always equal to voltage times current. If we substitute in our first relationship, what we'll find is that the power absorbed by an inductor is L times the current times the derivative of the current. So this is equation 3. And since energy is simply the integral of power, we can now develop a relationship for the energy stored by an inductor. Okay. So the energy stored by an inductor is going to be the integral of the power. And we're going to set the limits of integration here specifically to be from negative infinity to t. And I'll explain why we're doing those particular limits in a moment. So we're setting the limits here from negative infinity to t because we are assuming whenever this inductor was created, it didn't start having any energy stored in it. So that's effectively saying from some 0 energy level up to whatever energy is stored currently gives us the answer that we're looking for, okay? If we substitute in the equation that we just developed for power, we're going to have the integral from negative infinity to t of L I di by dt multiplied by dt, and all of these t's need to be primed. So any mathematicians in this room would be pissed off at me doing this, but for our intents and purposes, this dt prime in the denominator is canceled by this dt prime in the numerator. And so now we have a function who's varying with current as opposed to time. So I need to rewrite my limits of integration. So this is IL at negative infinity, which we assume to be 0, and IL at our current time, L IL DIL, which integrates easily, giving us 1/2 L IL squared. Where again, we have technically made an assumption here that there was no energy stored in the inductor at the beginning of time, which I feel is a pretty reasonable assumption to be made. So with our inductor, the current flowing through it is the most important piece of information that we can know, because the voltage drop across the inductor depends on the current flowing through the inductor. The power that's absorbed or supplied by our inductor depends on the current flowing through the inductor. The energy stored by the inductor depends on the current flowing through the inductor. Hayden. Because L is the symbol that we use for inductors. Yes, L is, scroll way back up here. L is inductance. So all of our T's are primed there because we had a T in our limits of integration. And so we can't have the same variable in the limits of integration as we have inside of our function. So I'm just using a dummy variable. So I'm not doing an integration. Like this is not the same as if you had, all right, let me put it this way. T prime does not equal the first derivative of T, and double prime wouldn't equal the second derivative and all that kind of stuff is what I'm trying to say. So this is a dummy variable. We did the same thing when we were dealing with our relationship for charge on the second day of class. So anytime that I'm doing a derivative in this class, I full on express the derivative as a function of whatever variable we are doing. All right. So we have these four equations that govern the behavior of inductors in any and all electrical circuits. Okay, just these four. We have fully described how these guys behave. What we are going to do now is take a look at what happens when we have multiple inductors in a circuit and see if we can develop any relationships to combine them, similar to what we did with resistors. So let's start with a series combination of inductances. Okay. So our symbol for an inductor, which I have not introduced until this point, is a coil. For you mechanical engineers, probably looks like a spring, and they are analogous circuit components. I don't know how many of you guys mechanicals are aware of this, but you can do a lot of the work that you do effectively by treating mechanical systems as circuits. So springs are inductors, proof masses are capacitors, which we have yet to talk about, and mechanical dampers are resistors in a mechanical circuit. So anyway, so we have this inductor L1, this inductor L2, this inductor L sub n, all connected in series like so. The total voltage drop across this series combination of inductances will simply be the voltage drop over each of the individual inductors. So the voltage drop over inductor L1 we'll call V1, the voltage drop over inductor L2 we'll call V2, etc. Here we have V sub n, and because all of these elements are connected in series, there is some common current I flowing through them. Okay. So if we apply Kirchhoff's voltage law, what we will find is that V of t is equal to V1 plus V2 all the way out to V sub n like so. We know that the voltage drop across an inductor is related to the current flowing through the inductor by the first equation that we developed. And so this is going to look like L1 di by dt plus L2 di by dt all the way out to L sub n di by dt, and we can lump all of those inductor terms together. Call this LEQ di by dt, where equivalent inductance is simply the sum of L1 plus L2 all the way out to L sub n. Or put much more succinctly, inductors in series combine like resistors in series. We don't have to learn any new math and tips or tricks here. Okay? Now let's consider a network that contains multiple inductors in parallel. If there is some total current I of t flowing into this parallel inductor network, then each inductor will carry its own separate current. Like so. And because all of these elements are connected in parallel, they all share the same voltage. Kirchhoff's current law tells us that our total current I of t is simply the sum of our inductor currents. And we know that these inductor currents are related to the voltage drop across the inductor by that second equation that we developed. So all of these I needed a 1 over Ln here, sorry. All of these representations have the same integral. So this looks like 1 over L1 plus 1 over L2 all the way out to 1 over Ln multiplied by the integral from negative infinity to t of v t prime dt prime or 1 over LEQ times the integral from negative infinity to t of vt prime dt prime, where LEQ is 1 over L1 plus, 1 over L2 all the way out to 1 over L sub n reciprocal, meaning that inductors in parallel combine exactly like resistors in parallel, which hopefully should make sense, because if inductors in series combine like resistors in series, how else would we expect inductors in parallel to combine? All right. So I've hit you guys with several equations and all that kind of stuff. Let's work an example problem or two together, and then I'll let you guys work on your in-class assignments. So voltage drop across an inductor is described mathematically as 0 volts for t less than 0 and 5e to the negative 4t volts for t greater than or equal to 0. Okay. Our inductance for this particular inductor is 250 millihenries. Okay. I just realized that earlier I did not tell you guys about the units of inductance, so we're going to take care of that right now. Okay. So 1 Henry is equal to let me double check here. Yes. 1 volt second per ampere, which is the same thing as 1 ohm second. This is the one that I usually use to help me figure out what's going on. Okay. So if IL of 0 is equal to 2 amps, I want us to figure out IL of t, the inductor current for effectively all times past 0. The power absorbed by the inductor. And the expression for the energy absorbed by the inductor. So, starting with part A, which of the 4 equations that I labeled for you guys do you think we should be using here? Two, because we know the voltage and we're trying to find the current. Absolutely correct. Okay. So we know that IL of t is 1 over L times the integral from t naught to t of VL of t prime dt prime plus IL t naught. So if we substitute in our values here, this is going to be 1 over 250 times 10 to the minus 3. And if a Henry is a volt second per ampere, then our unit should look like volts seconds here and amperes up here. So let's start with, are we okay with that? All right. Now we are going to integrate from our time at which the inductor current is known, which was 0. That's told to us right here. So we're integrating from 0 to some later point in time. So we're going to get a mathematical function here. And since our integral ranges from 0 to some later point in time, we're going to substitute in the value of our inductor voltage that corresponds to that interval, 5e to the minus 4t volts bt. And then I'm going to go back through and make sure that I'm using my dummy variables correctly. Outside of the integral, I will add my initial condition, 2 amps. All right, so how do I take the integral of an exponential function? I'm going to go to the next page here, and we're going to walk through these rules very, very briefly. Okay. So the integral of e to the alpha t is 1 over alpha e to the alpha t plus c, but I'm not a mathematician, so I don't give a shit about any of that hippie stuff. Okay. The derivative of e to the alpha t is alpha e to the alpha t. I'm hitting you with these two things because we are going to be using the ever-living bejesus out of them over the next several class periods, okay? So the level of calculus that I expect you to be able to effectively carry out for your next exam is literally this: taking the derivative or the integral of an exponential function. These are the rules, burn them into your brain, okay? So since we're taking the integral, and alpha in this case is the quantity -4, we are going to have 1 over 0.25, getting rid of that 10 to the -3 thing there, with these units. I need to be pulling out a factor of 1 over alpha. So that's going to be 1 over -4. What units do you guys think that quantity -4 has? So the argument of the exponential function should be a unitless quantity because e to the some number should just return a number, right? There we go. So if time is a quantity measured in seconds, the thing that's being multiplied by time has to have units of per second. So that the argument that's being passed to the exponential function is a unitless quantity, okay? So anytime we see something multiplied by time, we are going to expect that it has units of per seconds unless explicitly told otherwise. So why is this important? Well, we need this per second here to cancel out this second here. Without it, our units get all garbled up, okay? I'm going to go ahead and also take out 5 volts. I'm going to just pop that in up here so that these volts cancel out this volts, and we can see where current is coming from because the only unit that's surviving this operation is the amperes in the numerator, okay? So now I'm just taking the integral of e to the -4t. I've already pulled out the 1 over alpha part. And so what I have left here is just e to the -4t evaluated at t and 0, like so, plus 2 amps. So dealing with all those constant terms on the left-hand side, I have 1 times 5 over -4 times 1/4. So I believe that's just going to look like -5 with units of amps. And then I'm going to have e to the 4t minus e to the minus 4 times 0, which is 1. And this is something that I see a lot of you guys make simple mistakes on. E to the 0 is not 0. E to the 0 is 1. Plus 2 amps. And now we can effectively combine like terms. So we have -5 amps times -1. So it's going to be +5 plus 2 amps. So this looks like 7 amps minus 5e to the minus 4t amps. So this is what our voltage looks like. Excuse me, our current looks like. Obviously a current because it has units of amps. Okay. So as a function of time, this is what we got. Jonathan, how may I help you?
The original equation that 1 over L also multiplies plus IL of E.
No. No. So the 1 over L is only being multiplied by the integral portion. Yes. So that's another big mistake that we see here. So this bit right here isn't in any way, shape, or form part of that integral. So it's not being multiplied by the 1 over L. It's not inside the limits of integration or anything like that. It is that integral multiplied by 1 over L plus this other thing. A lot of people make that mistake, just to be very, very clear. So I'm glad that you asked it. All right, so here's our voltage. Now we need to find our power. Well, this is actually going to be considerably easier, right? So for part B here, power absorbed by an inductor is IL times VL, or L times IL times DIL by dt. So should we use the representation of power that I've underlined in red, or the representation of power that I've underlined in blue? I disagree. Why I disagree with that is because we already know what the voltage is. It was given to us. Why make it harder on ourselves re-deriving it? Right? In our problem statement up here, this is the voltage. If we do L di by dt, we are literally just going to get that same thing again, but it's going to take a lot more work to derive it than just taking it from the problem statement. Okay? So 9 times out of 10, I personally simply use power is equal to I times V based on what I'm given. Okay, it's pretty infrequent that I actually wind up having to use these other relationships. All right, so anyway, so for us, we have our current 7 minus 5 e to the minus 4t amps. We're multiplying this by our voltage, 5 e to the minus 4t volts. And so what's going to happen here? So we're just going to effectively, it's not even really foiling this thing out because there's not 2 terms in each of the bits. But 7 times 5 is 35. So we're going to have 35 e to the minus 4t, and then amps times a volt is a watt. And then we're going to multiply -5 e to the 4t amps times +5 e to the -4t volts. And so what that's going to give us is -25 e to the minus. So what happens when I multiply 2 exponentials together? You add the exponents. Absolutely correct. So e to the minus 8t watts. Power's done. Lastly here, we have the energy absorbed by an inductor, which is given by 1/2 L I squared. That's going to be 1/2 times 0.25 volt seconds per ampere times 7 minus 5 e to the minus 4t amperes quantity squared. Is going to look like 0.125 volt second per ampere. 7 times 7 is 49 minus 70 e to the minus 4t plus 25 e to the minus 8t amp squared. Running out of room here, so let's look at our units. So what happens when I multiply a volt second per amp times amp squared? I get a volt amp second, or power watt times seconds, which is a joule, right? So this is going to come out to be 6.125 minus 8.75 e to the minus 4t plus 3.125 e to the minus 8t joules. Up until this point, a lot of you guys have been playing fast and loose with the units and have been able to kind of make things work. It's no longer going to work. You're going to find out when you're doing your web work and all that kind of stuff that if you don't pay attention to your units, the numbers that you get are going to be wildly incorrect. So I would very strongly argue get into the habit of paying attention now and make your life easier. All right, I think that's enough out of me for today. So please work on your in-class assignment and I will be more than happy to help you with any questions you may have.